When you think about abstract mathematics, it's really easy to picture this pristine, untouched world.
Oh, absolutely, like a perfect vacuum.
Right. Just pure numbers and symbols floating in a void.
Yeah.
Completely perfect. But the reality is when you take those flawless mathematical concepts and drag them down into the messy, gritty world of computer software, things break.
They really do. They break hard.
Yeah. And today, we are doing a deep dive into a fascinating set of technical notes for a project called NetListX ASOCHP. And this project, it actually builds a functional bridge between perfect math and the chaotic reality of software engineering.
It's honestly the ultimate collision of theory and application.
Yeah.
Because what looks elegant on a chalkboard it can instantly crash a modern computer if you don't translate the logic carefully.
sir.
You have to account for memory, speed, and these constantly shifting environments.
Okay, let's unpack this. Because if you've ever tried to manage a massive system, whether that's, software architecture, logistics, or even just scheduling a huge team, you know that finding the absolute perfect solution is usually a myth.
It is.
You need a practical shortcut that won't fail when the pressure is on. And to understand how they achieve this in the NetListX CPP project, we first have to look at the battlefield they're operating on, which is electronic design automation.
Right, or ADA for short.
Yeah.
This is the software ecosystem used by engineers to design computer chips.
And chips are incredibly complex now.
Unbelievably complex. I mean, modern microchips contain billions of microscopic transistors. A human being cannot just sit down and draw that layout.
No, of course not.
You rely entirely on algorithms to determine the most efficient way to place those tiny components and wire them together so the chip actually functions.
And doing that requires tackling some intensely difficult math problems. The notes specify that the problems they are solving are NP hard. Now, I've heard that term thrown around, but practically speaking, does that just mean it's literally impossible to solve?
Not impossible, but computationally unreasonable if you want an exact answer.
Okay.
NP-hard basically describes a problem where calculating the single, absolute, perfect solution scales so poorly that, well, for a chip with billions of connections, the universe would end before your computer finished checking every possible layout.
Wow, so exact solutions just completely fail at scale.
Exactly. They just hit a wall.
So we need a shortcut, a really highly accurate shortcut. And the specific class of problem they are trying to approximate here is called a covering problem.
Yes.
Which sounds like total alphabet soup in the raw notes. Finding a minimum weight subset C of vertices out of a larger set V.
It does get a bit dense.
It does.
Yeah.
So let's get out of the textbook for a second. Let's think about it like you are the head of security for a massive, sprawling art museum.
Okay, I like this.
The museum has hundreds of long hallways, and those hallways intersect at various little plazas or rotundas. And your non-negotiable constraint is that every single hallway must be watched by at least one security guard.
Right, no blind spots.
Right, but you have a very tight budget, so you want to hire the absolute minimum number of guards possible.
That is a brilliant visualization of a standard vertex cover problem.
Thanks.
The intersections, those are the vertices. The hallways are the edges or the constraints you have to satisfy.
Okay.
And you want to pick the minimum number of intersections to stand a guard in, ensuring no hallway is left in the dark.
And in the reality of chip design, these covering problems show up everywhere. They just, wear different masks. The notes mention hypergraph vertex cover, cycle cover, and odd cycle cover.
Yes, and understanding why these matter physically is crucial. Take hypergraph vertex cover, which is used for netlist partitioning.
What does that mean in physical terms?
Well, a netlist isn't just a simple wire connecting point A to point B. It's often a broadcast network, one source feeding a signal to thousands of receivers simultaneously.
Okay.
So if you have to physically divide the layout of a chip into smaller modules to actually manufacture it, you need to find the absolute minimum number of cuts that touch every single one of those complex broadcast nets without severing critical communication lines.
Got it. And what about cycle cover? The notes say it's used in logic synthesis.
This one has very high physical stakes. In a complex circuit, you occasionally create unwanted feedback loops.
Like an audio echo.
Exactly like that.
Okay.
A signal inadvertently loops back and feeds into itself. And if you leave that loop in the physical hardware, the chip essentially traps itself in an endless echo chamber.
Oh, wow.
Yeah, the signal oscillates infinitely, it burns massive amounts of energy, and the processor just hangs. The hardware literally crashes.
That sounds bad.
It is. So the cycle cover algorithm finds the absolute minimum number of physical wires you need to snip to break every single feedback loop in the entire system, rendering the chip stable.
So you're surgically removing the infinite loops and the odd cycle cover.
That's used for bipartite structuring. Imagine trying to color a map with only two colors without any bordering countries sharing the same color.
Okay.
If you have a triangle of bordering countries and an odd cycle of 3, it's mathematically impossible.
Because two of them will always match.
Right. So odd cycle cover identifies and removes those odd numbered loops. Once they're gone, you can neatly divide the remaining network into two distinct alternating sets, which is vital for certain optimization tasks like max CUT.
Okay, so we are dealing with massive, physically critical networks. But hold on, if we go back to our museum analogy,
Sure.
we established that finding the absolute perfect guard placement is NP hard, meaning it's computationally impossible at this scale. If we can't find the exact answer, aren't we basically just guessing? Doesn't that risk leaving a hallway totally unmonitored?
No, and that is a crucial distinction. We are not guessing. We are using what computer scientists call guaranteed approximation algorithms.
Okay.
What's fascinating here is how the algorithm provides a mathematical certainty that its shortcut answer will never exceed a strict limit.
Oh, interesting.
Yeah, it guarantees that the number of guards you hire will never be worse than, say, exactly twice the perfect minimum. It puts a hard, provable ceiling on how wrong the approximation can be, while still guaranteeing every single hallway is watched.
That makes a ton of sense. It's bounding the error. So how does a piece of software actually pull that off? The source materials introduce a toolkit for this called the Primal Dual Framework.
Right. To understand the primal dual framework, you have to picture the algorithm playing a game against itself.
Okay.
It doesn't just build one solution, it builds two simultaneously. The primal solution is the actual answer you want, the guards you were placing in the museum. But alongside it, it tracks a dual solution.
And the technical presentation calls this dual solution gaps. And they use a really striking visual metaphor to explain the mechanics here. They call it the gap bucket.
I love this metaphor. Imagine every single intersection in your museum has a physical bucket sitting on the floor.
Right. And every intersection has a different weight or cost.
Right.
Maybe some intersections are huge and require an expensive, highly trained guard.
Exactly.
So that cost determines the size of the bucket. A really expensive intersection gets a very tall bucket. A cheap intersection gets a short, small bucket. At the starting line, all the buckets are totally empty. The empty space, the gap between the bottom of the bucket and the rim, represents the full cost of hiring that guard.
Spot on. The algorithm begins by scanning for violated constraints, unwatched hallways.
Okay.
Whenever it spots a hallway without a guard, it looks at the intersections at both ends of that hallway. It then starts dripping water equally into the buckets at both ends.
And as the water drips in, that empty space, the gap, shrinks.
Exactly.
Yeah.
And the moment the water level reaches the very rim of a bucket, the moment the gap hits zero, that specific vertex is considered fully paid for.
Oh, I see.
The algorithm instantly hires a guard and places them at that intersection. That vertex is added to the primal solution.
Wait, I'm losing the thread here slightly. If an intersection connects to 5 different unwatched hallways, is it getting water dripping in from all 5 simultaneously?
It is, yeah.
Wouldn't a highly connected intersection just flood immediately then? How is that actually helpful for making a smart decision?
That's not a bug. That's the core engine of the logic. It's a mathematical property called complementary slackness.
Complementary slackness.
Yes, an intersection connected to 5 unwatched hallways gets 5 drips of water for every 1 drip a less connected intersection receives. Its bucket fills incredibly fast.
Oh, I see. It's a race to the rim.
Precisely. The dual solution, the dripping water, creates a natural, localized gravity. It inherently forces the algorithm to prioritize hiring the guards who can watch the most hallways at once.
That's super clever.
You don't have to scan the entire multi-billion node network to find the best candidate. The local water levels naturally push the most efficient intersections over the finish line first.
Because it's localized, you don't need a massive overarching calculation. The notes show this operates in linear time, bounded by the dual cost.
Right.
The bigger the chip gets, the algorithm's runtime grows relatively slowly, which is exactly the performance you need for EDA.
But there is a catch.
There's always a catch.
The primal dual phase successfully guarantees every hallway is watched. But because multiple buckets are filling simultaneously from different sources, the moment a bucket overflows and a guard is hired, you might realize a fraction of a second later that a neighboring guard was also just hired.
So we overhired. We have redundant guards watching the exact same empty hallways. The solution is safe, but it's sloppy.
Exactly. We need a cleanup phase. The presentation refers to segment 3 of this logic as the reverse delete mechanism. We need to trim the fat without accidentally leaving a hallway unprotected.
Here's where it gets really interesting, because the cleanup logic feels almost backwards, but mathematically it's bulletproof.
It really is.
The algorithm takes the master list of every guard you just hired during the bucket phase, and it iterates through that list in the exact reverse order they were hired.
The very last guard you placed on the payroll is the first one you evaluate.
You look at that last guard, and you temporarily pull them off the floor. You delete them from the cover. Then you test the alarm system. Did any hallway suddenly go dark? Did a violation reappear?
If the alarm stays silent, it means that guard was completely redundant. Other guards who were hired earlier in the process are already watching all of those hallways.
So they aren't needed.
Right. Since the guard is useless, they stay deleted. You've pruned the network.
But if you pull the guard off the floor and an alarm immediately blares because a hallway is now completely empty,
Then you know that specific guard is mathematically essential. You immediately put them back on the floor and you move to the next person on the reverse list.
the slide deck proves how powerful this is with something called the K5 test, which is a complete graph of 5 vertices, right?
Right. Where every single vertex is directly connected to all the others.
Yeah, so it's this incredibly dense knot of 10 edges.
It's the ultimate stress test for redundancies.
Right. So let's imagine we run the bucket phase on this K5 knot. And because it's so dense and messy, the algorithm gets sloppy and accidentally hires all 5 guards.
Yeah, that's common.
So we move to reverse delete, we walk backward, we pull out guard number 5 and check the alarm. Well, guards 1, 2, 3, and 4 is still there, and since everyone is connected to everyone, they easily cover all 10 edges.
True.
Guard 5 is redundant. He's fired.
So we are down to 4 guards.
Now we test guard number 4.
Hmm.
We pull her off the floor. Suddenly, we only have guards 1, 2, and 3.
Mm-hmm.
In a K5 graph, 3 vertices can only cover 9 edges. One edge, the one connecting vertex 4 and vertex 5, is completely unwatched. The alarm goes off.
Math kicks in.
Exactly. The algorithm realizes guard 4 is critical.
Oh.
It puts her back. It tests 3, puts him back. It tests 2, puts him back. You end up with exactly 4 guards.
Yes.
And mathematically, a minimal cover of a K5 graph requires exactly 4 vertices.
Yes.
The reverse delete perfectly trims the sloppy approximation down to its absolute leanest mathematical minimum.
And when you combine the primal dual bucket selection with this reverse delete cleanup, you achieve a theoretical 2 approximation for vertex cover. It is an ironclad, mathematically proven guarantee.
On paper, it's brilliant. But this is the point in the deep dive where theory hits a brick wall. When software engineers actually sit down to write this flawless math into a computer language, the whole thing shatters. The technical notes call this the implementation hurdle.
Yeah. If we connect this to the bigger picture, what they hit is a classic, terrifying computer science paradox, operating on data that has already changed.
Oh man, the presentation breaks down the naive way a standard programmer might try to code this. They call it the all-at-once approach.
Right.
You look at the math and say, okay, step 1, I'll write a function that scans the entire chip and finds every single feedback loop, every single violation. I'll make a massive master list of them. Step 2, I'll just write a basic loop to go down that list one by one, drop the water into the buckets, hire the guards, and fix the chip.
The fatal flaw here is state mutation. You cannot use a static list in a dynamic environment.
What does state mutation actually look like when the code is running? I want to visualize the crash.
Well, let's say your master list has cycle A and cycle B on it. Your code looks at cycle A, it drops the water in the buckets, a gap hits 0, and you select a vertex to cut. You snipped a wire.
Okay, loop A is broken, the chip is safer.
But the physical act of snipping that wire fundamentally altered the layout of the entire chip, which means cycle B, which was sitting patiently on your master list, might not even exist anymore. Or its shape has drastically changed. The underlying reality has mutated. But your simple code loop doesn't know that. It moves down the list and blindly attempts to process cycle B. It reaches for a memory address that no longer exists, and the entire program crashes.
It's like navigating a magical maze. You stand at the entrance and draw a perfect map. But the moment you take a single step forward, the walls of the maze physically shift and rearrange themselves.
That's a great way to put it.
If you just keep staring down at your paper map and blindly walking the path you drew 10 seconds ago, you're going to slam face first into a solid wall. Your map is stale data.
That is precisely the danger. Pre-computing all the violations is a death sentence because resolving one violation inherently mutates the graph state for all the subsequent ones.
So the obvious fix seems to be, well, throw away the map after every single step, find one cycle, fix it, and then completely recalculate the entire multi-billion node chip from scratch to find the next cycle.
You could, but from an engineering standpoint, it's a nightmare. Recalculating the entire graph from scratch every single time you snip a wire would destroy the linear time complexity we were so excited about earlier.
Right.
It would take weeks to run. You lose all your speed.
So how do you avoid slamming into the shifting maze walls without, slowing down to redraw the map every single step? This brings us to the real hero of the Netlist Take Softy project. They solved this paradox using cutting-edge software architecture.
Yes.
Enter modern C++20.
Specifically, they leveraged a feature called C++20 generators, utilizing a programming concept known as lazy yielding.
Lazy yielding. I mean, how does being lazy keep us from crashing into walls?
Instead of a static master list, the solution uses a coroutine. Think of a coroutine like a specialized conveyor belt that can hit pause without losing its memory.
Okay.
In the execution trace provided in the notes, a generator function explores the graph and finds just one single violation. Let's call it S1.
It spots S1, and then the code literally says coyield S1.
When the generator hits that yield keyword, it hits a hard pause. It entirely freezes its own execution state. It keeps its place in the maze and hands S1 over to the main algorithm.
The main algorithm takes S1. It processes it, it drips the water, hires the guard, snips the wire. It mutates the state of the graph. The walls of the maze shift.
Once the main algorithm is finished, it reaches back to the frozen generator and hits a resume. And here is the absolute magic of a coroutine. When the generator wakes up, it is immediately viewing the freshly updated state of the graph.
Oh, that's brilliant.
Right. It looks at the new reality, the new maze walls, before it takes a single step to find violation S2.
It's pausing, letting reality update around it, and then taking a fresh look. There is no master list. There is no stale map.
Exactly.
It permanently prevents the stale data crashes without the massive, slow overhead of recalculating everything from scratch.
It is a breathtakingly elegant solution to state mutation. It preserves the stack frame of the search while dynamically absorbing the changes.
So what does this all mean for the end product? Because the presentation highlights that by solving this with lazy yielding, they accidentally created a universal engine.
Well, it wasn't an accident. It's the pinnacle of decoupling the what from the how.
How so?
Because the generator is isolated, the core mathematical engine, the function they call auto PD cover, is completely invariant. The complex logic of the gap buckets and the reverse delete cleanup is locked in a vault. It never changes.
But the way you find the violations does change based on the EDA problem.
Exactly. You just plug in different domain generators. You plug in a generator that yields edges, and the engine solves vertex cover. You plug in a generator that yields broadcast nets, and the exact same engine solves netlist partitioning.
So one core mathematical engine solves four completely distinct, incredibly complex physical hardware problems with absolutely zero logic changes inside the main loop.
Pretty incredible.
The presentation notes they achieved Python-like elegance, but they built it in hardcore, hardware-accelerated C++ splitter.
Which is an immense technical achievement. Python is beloved because generators are native and easy to read, but Python is notoriously slow for billions of calculations.
Right, you need speed here.
C++ is lightning fast, but the syntax can be dense and brutal. By utilizing C++20, they ported the elegant Python coroutine logic over in a one-to-one translation. Pure, fast, modern code with zero external dependencies.
To synthesize this incredible journey for you listening, we started with a computationally impossible reality. NP hardware problems where finding an exact answer would outlast the universe.
Right.
We approximated those problems using the beautiful localized math of the primal dual framework, letting the gap buckets naturally highlight the most efficient solutions through complementary slackness.
And then we mathematically guaranteed the leanness of that solution using the reverse delete mechanism, pruning out the redundancies by walking backward and testing the alarms.
And finally, we translated that chalkboard math into flawless software using modern C++20 lazy coroutines. We completely bypassed the trap of stale data by pausing, acting, and observing the new reality before moving forward.
Whether you are writing backend code, designing physical architecture, or managing massive complex teams, decoupling the definition of the problem from the engine that resolves it is the ultimate architectural takeaway. It creates systems that are resilient, adaptable, and safe by design.
I love that.
But this raises an important question. If this concept of lazy yielding is so incredibly powerful for navigating shifting environments in computer science, where else could we apply it?
That is a thought worth sitting with. Think about human organizations. Think about highly volatile, rapidly mutating markets. So often, leadership teams default to the all-at-once approach.
Oh, all the time.
They pre-compute a massive 5-year strategic master list of initiatives, and they just blindly execute down that list, even as competitors launch new products and the very structure of their industry mutates around them.
Yeah, they're confidently following a stale map into a wall.
Exactly. If computer science is moving toward lazy yielding, literally designing systems that explicitly pause to observe a dynamically changed environment before taking the next step, could human organizations use that exact same framework to make better decisions? What would a core routine look like for the team you manage? Something to mull over as you navigate your own shifting mazes this week.